Let's do a quick review of what we know about the normal curve. We know that it is centered around mu, and that each of these little tick marks is going to be one standard deviation away from the last. The ones that are below are going to be down by sigma, down by 2 standard deviations, and then 3. The empirical rule gave us the probabilities of 68%, 95%, and 99.7%. But even more useful is probably labeling each of these little segments in the normal curve. And then we can find probabilities using those numbers. For example, if our BMI for a 60-year-old male, the average is 29 and the standard deviation is 6, the probability of a randomly selected 60-year-old male having a BMI of less than 35, all we would do is we would calculate the area that's to the left of that 35 mark. We know that this chunk right here is 50%, and then this is another 34% right here, so we've got a total of 84%. Between 17 and 23, that would be between here and here, which corresponds to that 13.5% probability. And then finally, greater than 47. 47 is actually 3 standard deviations above the mean, so there's just a very tiny little area in the tail of that curve, and that area represents 0.15%, a very low probability that a randomly selected male will have a BMI of over 47. Here's another example. The weights of babies at birth are normally distributed. It is reported in one study that 95% of full-term babies of European descent are born between 6.3 pounds and 9.9 pounds, with the average weight being 8.1 pounds. So they've told me that mu is 8.1 pounds. And I could start drawing my normal curve then with the 8.1 centered right here. It says that 95% of full-term babies are born between 6.3 and 9.9. We know that that 95% is 2 standard deviations away from the mean. So that's where the 6.3 and the 9.9 should go, because of that 95% from the empirical rule. So then we can probably figure out what sigma is, right? This is up by 2 standard deviations for a total of 1.8 pounds. Half of 1.8 pounds is 0.9 pounds. So if we count each of those spaces as 0.9 pounds, that should get us right where we wanted to be. Now it says that 68% of babies weigh between what and what at birth. That 68% is again 1 standard deviation from the mean. So 68% weigh between 7.2 and 9.0 pounds. Now what if we want to talk about a baby weight that isn't a whole standard deviation away, like an 11-pound baby? I know an 11-pound baby would be just a little over 3 standard deviations from the mean. But can you calculate how many standard deviations away it is? It's going to be 3 point something. Maybe one way to think about it is we could think algebraically. 8.1 plus this many sigmas to get us to 11 pounds. Subtract the 8.1 and divide by 0.9. And I get 3.2 repeating. We're normally going to go to 2 decimal places on that, so we'll call that 3.22 standard deviations above the mean. Now could I find the probability of a full-term baby of European heritage being born between 10 and 11 pounds? Well, that's a little tough, right? Because we don't have an 11 really marked on here, and 10 is about right here, but if we could somehow calculate the area under the curve from 10 to 11, then that would be the probability. Wait, there have to be values assigned to probabilities that don't land on whole number standard deviations from the mean. How can we find the areas of awkward intervals? They did all that work for us. Table 3 and 3a in the back of your book have hundreds of probabilities already worked out. Wait, there are tables in the back that just happen to be for European baby weight statistics? Well, no, see, it's not the weights themselves that give us the probabilities, it's the distance from the mean in standard deviation units. Oh, that makes sense. Like when we figured out that an 11-pound baby was 3.22 standard deviations higher than the mean. Exactly. We call that the baby's z-score. Since 11 pounds is above average, z equals positive 3.22. A below average baby would have a negative z-score. Hey, I bet an average baby has a z-score equal to 0. That's right, the official formula is like this. Z equals x minus mu divided by sigma. Let's practice that formula. Z equals x minus mu divided by sigma. So if we were calculating the z-score for this 11-pound baby, we would take 11 minus 8.1 and then divide by 0.9, which is exactly what we did when we did that little algebraic move. And so that 3.22 is called the z-score for the 11-pound baby. We could do the same thing and find a z-score for the 10-pound baby. Just taking 10 minus mu divided by the standard deviation. Now, why are we doing that again? It's because we want a way to find the area right here. They can't have every possible normal curve figured out, so they have every possible z-score figured out instead. Let's start a new example. The time it takes for a pizza to be delivered is normally distributed with a mean of 25 minutes and a standard deviation of 2 minutes. What is the probability that we order a pizza and it comes before 22 minutes, that the time is less than or equal to 22 minutes? So a great way to do this is to, instead of talking about t being less than or equal to 22 minutes, we're going to calculate what z-score goes with that 22. So we know that z equals the x value, or the t value, minus mu divided by the standard deviation. And we get negative 1.5 for the z-score. So instead of calculating the probability that t is less than or equal to 22, we're going to calculate the probability that z is less than or equal to 1.5. That's the probability we're looking for. So when we look at this table for areas of standard normal distributions, you'll notice that the mu is centered at 0 because the average is going to be 0. And then our z-score, which in our case is negative 1.5, is already calculated as a less than or equal to probability. That's how this table works. And so we are going to go down to where it says negative 1.5, and it's negative 1.50, right? I said 2 decimal places. So we'll go down to negative 1.5, and we're looking at the negative 1.50 column. And so this is the probability that we're looking for. 0.0668. So there is a 6.68% chance that our pizza will come before 22 minutes. Let's try one that's a little more challenging. We're going to find the probability that our pizza comes between 24 and 26 minutes. So we're going to need 2 z-scores here. One for the 24 and one for the 26. Remember, I'm just using that z-score equals x minus mu divided by sigma. So there's no table for the 24 and the 26 because those are time values. But if we convert that over to z values, z-scores, then we'll be able to use the table to find that. Now there is one little problem. Remember that 0 is right in the middle, so negative half a standard deviation would be just a little bit to the left, and positive would be just a little to the right. So we're trying to find the area between here and here. Should actually be nice and symmetric, right? And it's not going to be as high as the 68% because we didn't go a full standard deviation away from the mean. But the catch is that the table only calculates the less than or equal to's. So I could calculate this part of the area really easily. I could even calculate the 0.50 and down really easily. Well, would you believe that the area between those two numbers would be the same thing as taking the area from 0.5 and down, and then just subtracting off that extra part right here we don't need. So we would be subtracting off anything less than or equal to that negative 0.50. And that would leave us with just the chunk that's between those two. So when we go to the table, we will find the probability that z is less than or equal to 0.50. That'll be this area under the curve. But then we will subtract off the probability that z is less than or equal to negative 0.050, which would be this area. And that should leave us with just that chunk that we need. So we're back to the table. I have the negative version on this first page, negative 0.5, and then 0.50 would be this value. And then if you go to the next page, that's where you're going to find the positive ones, right? So we're looking for where that z-score was 0.50, and we're going to figure out that entire area. 0.50 would be 0.6915. So this big area is 0.6915, and that smaller chunk was the 0.3085. So there is a 38.3% chance that our pizza comes between 24 and 26 minutes. This next one will be a little bit simpler. Step 1 is to convert that t to a z-score. So that represents a really fast time, 2.5 standard deviations below average. And I would say most pizzas are going to take more than 20 minutes to arrive, wouldn't you say? But again, when I go to the table only gives me the less than or equal to's. But in this case, we can just think of it as an easy complement, right? What's the opposite of being greater than or equal to negative 2.5? The complement 1 minus the probability of z being less than negative 2.5. And less thans we can do using that chart. It actually really doesn't matter that it's not less than or equal to. We're just talking about the area under that curve, so we don't need to worry about when the value is equal to negative 2.5. So we'll go to the chart now and we'll find the probability that z is below negative 2.5. Negative 2.50 is 0.0062. So this little chunk, very small, 0.0062, 1 minus that will give me the area that I was looking for, where the z-score is above negative 2.5. And I was right, most pizzas are going to take longer than 20 minutes, 0.9938. There is a 99.38% chance your pizza will take longer than 20 minutes to arrive. Next one, what does z equals 3.2 represent? Would that be a delivery time that is longer than usual or shorter than usual? Since that's a positive 3.2, that should be above average. And we could use the z-score formula to kind of interpret that. We know that z is 3.2. We know mu is 25, and we know sigma is 2. So we could do some simple algebra. Take that 3.2 times 2, and then add 25 over. And the reason I wrote it out like that is because I wanted to show you that we are talking about 3.2 standard deviations above average. So we started at the average and we added on 3.2 standard deviations. And that comes out to 31.4, so really that represents 31.4 minutes in delivery time. There is less than a 10% chance that your pizza will come before how many minutes? Do you recognize this, that they're having us solve for what the z value would be this time? We're going to try to figure out what z-score corresponds to less than a 10% chance. So we're going to go to the table, and this time we already know the probability, and we're going to be trying to search for the z-score. So again, in this case, we actually know the value of the probability, and we're going to try to figure out which z-score goes with it. Can you help me find 10% in this chart? I guess this is like 1.25%, right? Here's 5%. So we're going to try to find as close to 10% as we can get. 0.09 is pretty close. 0.098 is even closer. 0.10, okay, I think it's between these two values. Do you see what I mean? If I were looking for 10%, this one's just a little high and that one's just a little low. But remember, I am looking for something that is less than 10%. So I think we're going to go with that 0.0985. And what z-score does that correspond to? We're at negative 1.29. Negative 1.29 corresponds to that probability. So now that we know the z-score, we should be able to calculate what that means in minutes for the delivery driver. Since the z-score is negative, that means it's going to be below average. How much below average? 1.29 standard deviations below average. We could set up that little z-score formula again, or we could just think it through. I know that the time is going to be shorter than 25 minutes. How much shorter? 1.29 standard deviations shorter. There is less than a 10% chance that that pizza is going to come sooner than 22.42 minutes. I just want to make sure that you understand what they mean when they say a standard normal distribution. A standard normal distribution is when they take all of your means and standard deviations and they standardize them. And so your mu will always equal 0 on a standard normal. Again, that's on a z-score. And if we go above the average by 1 standard deviation, 2, and 3 standard deviations, we would actually be talking about a standard deviation of 1. So that would literally be 1, 2, 3 on that number line. And negative 1, negative 2, negative 3 on that number line. So all of these table values are based on this standard normal curve where those z-scores are aligned so that the mean is at 0 and the standard deviation is normalized or standardized to 1. Standard normal distribution. Same shape, same empirical values, just having those z-scores instead of x. Let's go back to that baby weight thing. Remember on the first slide we talked about how mu was 8.1 pounds and we figured out that the standard deviation was 0.9. I'm going to show you another way to find these probabilities not using the table. We'll practice again using the table too. So one way to figure out the probability that a weight is above 10 pounds would be finding that z-score. And then instead of calculating that for the weight being 10 pounds, we'll be calculating for the z-score being 2.11. Again, that table won't let us do greater than, so we'll take the complement of that. 1 minus, what's the opposite of greater than 2.11? Less than or equal to 2.11. Not paying too much attention to that, or equal to. Here is 2.1, and 2.11 is right below this. So that's lining up at 0.9826. So we're talking a 1.74% chance that you're going to have a baby that weighs more than 10 pounds. They're kind of rare. Now, would you guess that there's a calculator button that can help us do this as well? The calculator button we'll be looking for is not binomial PDF like last time, but normal. And we're going to use CDF because we're talking about these greater than or less thans. And we'll find that in the same spot as before, second vars under the distributions, and then there are right at the top, normal CDF. Now, if yours doesn't ask for lower upper mu sigma, just know that that's what you're going to need to enter as your 4 numbers with commas between. And actually, we can even use the 10 pounds to do this. We don't even need a z-score if we're going to use our calculator. So if I were talking about W, the weight, being greater than 10 pounds. The lowest weight that I'd be looking at is a 10-pounder. The heaviest baby I'd be concerned about is a 999,000. Just put the, if I could put infinity right there, I would. Just put a huge number. So I'm talking about a baby that weighs between 10 pounds and way more than that. That's going to be basically the same idea as a baby weighing greater than 10 pounds. And since I'm using weights, I'm going to want to go back and put in that actual average weight in pounds. Same thing for the standard deviation. When I push enter, it gives me 0.0174. 0.0174. Isn't that beautiful? So we found that same answer without having to deal with z-scores or the table. Once again, we want to do the low, comma high, comma mu, comma sigma. That's the entries that we're looking for. So in this example, I went the low as 10, the high as 99999. Mu is 8.1 and sigma is 0.9, and it just spit out the right answer. So easy. Let's do that again. Let's do that to figure out the probability of finding a baby that is so big that it's between 11 and 12 pounds when it's born. I wonder if any of you were big babies. So when we do our normal CDF, the low would be 11, the high would be 12. We're just looking for the probability of being between 11 and 12. We know mu is 8.1 and sigma is 0.9 pounds. Second vars, normal CDF. And that's a really low probability, right? 6.29 times 10 to the negative 4. If I round that to 4 decimals, which is what we usually do, that would be 0.0006, which just means that a baby between 11 and 12 pounds when it's born is quite rare. Only a 0.06% chance of that happening. I kind of like that, staying away from the z-scores and making the calculator do the work. Now remember, if we were going to do a z-score on that one, we'd have to find the probability of x being less than 12 and then subtracting off the probability of x being less than 11. But we'd need to convert those both to z-scores in order to use the table. So definitely still doable, but it'd take a few extra steps. This next one wouldn't be too bad using the table. All we would need to do is find a new z-score for that, and the table is already set up for less thans, so that would be pretty simple. But let's talk about how that would look on the calculator. If I were trying to find a really tiny baby, a baby that was born less than 5 pounds, if I were looking for the low and the high, what would the low be? You might say 0 pounds, but just to be safe, let's think of the biggest negative number we can think of. Like I said, I would use negative infinity if I could. So I'm going to just use a super low number. And yes, I realize a baby can't weigh that much when it's born. So that's the low, and this would be the high. The 5 pounds would be the high. The 8.1 and the 0.9. I'm just curious, what would have happened if I did put 0 pounds as that low value? You know, it's almost the same, but it was definitely safer to use that super, super small number, but in this case, it didn't really matter. And I'm looking at a very low probability again, 2.9 times 10 to the negative 4. To 4 decimals, again, a very low probability of having that tiny of a baby. Okay, now I'm just curious what kind of z-score that baby would have. The z-score again is the x value minus the mu divided by the standard deviation. How tiny of a baby is this? Well, that is very tiny. Negative 3.44 standard deviations. 3.44 standard deviations below average. Tiny little baby. And just out of curiosity, if we go to the table, negative 3.44 came out to 0.0003. So maybe the table would have been just as quick for that one. Okay, let's talk this super large baby. Greater than 15 pounds. So the low and the high, the lowest I'm interested in is that 15-pound baby. Now I need a very high weight. I'm just going to throw in a bunch of 9s. My goodness, that's a small number. 8.9 times 10 to the negative 15. So even if we move that decimal place over 15 spots, if we're only rounding to 4 decimal places, it'll just be 0.0000. There's really hardly any chance that you're going to find a baby that's born greater than 15 pounds. I do want to show you what happens when you do the z-score version of that. How big of a baby is this? Yeah, that's a massive baby. 7.67 standard deviations above average. And where can we find that number on the table? 7.67. And look at this, our table maxes out at 3.49 actually. For z values greater than 3.49, use 100%, 1.000 to approximate the area. But remember, that's for less than. So if we're going to say that the probability of being less than 15 pounds is 100%, then the probability of being greater than 15 pounds would be 0%, rounding to 0. So once we get beyond 3.5 standard deviations from the mean, that's when we're in those tiny little tail areas at the edges of that normal curve. There's hardly any area under there once you're 3.5 standard deviations away from the middle.